going to talk a little bit, just to give a short historical perspective on what technologies have been used in the past 20 years. I'll talk about the basic fundamentals that we use for electromagnetic induction. And then we'll talk about the traditional DGM, advanced geophysical classification, and then I'll revisit DGM in light of what the advanced sensors can do for us. So in terms of historical perspective, I have a little analogy here. We have the original phones. They were analog. That's what detect and dig does. They got the job done. Very simple to use. Very reliable. Detect and dig, I put tried and true. It's tried and true, but we also know that it's not perfect. We know that there's you're not going to get 100% detection. The other disadvantage is there's no digital record, and without a digital record, it's not conducive to quality management as we envision quality management should be. Following that, in the mid-90s, just recently we had DGM. And DGM is a process where you go through and you actually map the site. And the advantage of this, it provides a digital record, so it is conducive to quality system controls. You get much better detection performance, but now that we've detected it, more things, it actually is more expensive because you have a lot more data. And you have to do it twice. You go out and do the detection survey, then you have to back out and take it back. And so recently, there's been a lot of buzz about AGC, out of advanced geophysical classification. I don't know why they use the term advanced, because sooner or later it's not going to be advanced. But they decided to stick with it. So again, it provides a digital record. It also has the advantage of reducing unnecessary digs. And it came with it, because we're leaving things in the ground, we had to use a much more mature quality management system to manage it. And I'll talk tomorrow about the quality management systems. The side effect of this quality management system, you get a realistic prediction and assessment of your performance after the fact and before the fact. It is not suitable for all sites. We have to be very clear about that, and there's a non-trivial learning curve associated with it. And we'll talk. Okay, EMI basics. I don't know how many people know this. It's kind of simplified in its cartoon form. We have the EM sensor has two loops, a transmitter loop and a receive loop. Sometimes it can be the same coiled wires that does the same thing, but we have two, much like metal detectors you see on the beach, people waving around. It's the same thing. In the time domain systems, which are the ones that are primarily used, we turn on the primary field. It energizes the area around it. If there's a piece of metal, it will induce eddy currents. When we shut off the primary field, we can measure the eddy currents as they decay. So here, this is the green box. That's what we're interested in terms of measuring the EMI response. And so I have the same kind of area plotted here. It's a different scale. Because it decays so quickly, we use a log scale for the vertical axis. But if you think of it like just energy dissipation, like a cup of hot coffee where the heat dissipates with time, it's the same concept. The amplitude, how far it can go on that axis, and how far out the signal extends, is related to both extrinsic features, how far you are away from the sensor, what the orientation is relative to the sensor, and the intrinsic features, how big is the object, what's the object shaped like, and what is it made of. So, going to digital geophysical mapping, this is a typical sensor, the EM61 sensor, where it measures the decay at 4 discrete points. And you can see, where these decay are. The red part on this little image is where we're measuring decay with our advanced sensors. And the EM61, these green lines are where we're measuring the EM61 sensor. So we get for every measurement, you'll get 4, they call them time gates. You'll get measurements of 4 time gates. And what you do is you map one for a combination of these time gates. You assign the value, you map it with, you georeference it, and then you'll see you plot along each path that you traverse, because you go and you survey the grid with cutting along, and you cover everything with the sensor. They take these and what they do is called gridding. And so they interpolate the responses from their measured position to regularly spaced grid nodes. And you can select targets based on the gridded response or based on the profile representation of the target. Now there's pros and cons for both methods, right? The gridded response, you get one nice peak for a target. Here, this is a bigger response. We don't know if there's one or more targets, and the peak should occur roughly over the target, depending on some things I'll talk about later. But in the profile, you would get, for this target, you'd get a response here, here, here. This profile is the response going along this line that I've highlighted. But you can see here, there's an extra peak here. That peak, this peak is occurring here, and that second peak is occurring over here. And that may or may not be a second source under that anomaly, or it may be due to a horizontal cylinder that's tilted. So some definitions, just to be clear. Anomalies are responses in the geophysical data set. You can't go dig an anomaly. We all say we do it, but you can't. You dig the targeted location that you've discovered by finding the peak of the anomaly. Where is that peak located? So the target are basic dislocations that are targeted for further investigation. It can be an intrusive investigation, it could be acute investigation with an advanced sensor, but we're just saying, okay, we found something, we need to understand what the source of that is. When I use the word source, that's the discrete metal object that we're worried about. That caused the anomaly. And then the concept of signal to noise, it should really be talking about detection. Detection is a function of signal to noise. Right? We can model with the various sensors we have what the signal is going to be. We only know if we can detect it if we know what the site noise levels are. And that's a critical concern here. So we'll talk about detection considerations. This concept that I referred to as maximum reliable depth of detection. That's the depth at which the signal to noise is roughly 5 times the background noise. The signal is 5 times the background noise. When the object is in its worst case orientation and position under the sensor. Okay, so if the object is, if it's a cylinder and it's vertical, in the center of the sensor, that's when it's maximally coupled to the primary field, you get the biggest signal. When it's horizontal, it's minimally coupled, you get the smallest signal. Off to the side, depending on its orientation, it can be maximum or minimally coupled, but it's minimally coupled off to the side of the sensor. That's the case that we're interested in. That's depth. So as long as you get the signal to noise ratio of 5 at that depth within that location, you're going to reliably detect those objects. This is a very important concept during planning that you have to make sure people understand, or people that are doing the work, to make sure that they're telling you what their maximum reliable depth of detection is going to be. And you have to reconcile it with how deep you want to look. Right? Because if you can't see deep enough with these sensors, you have to plan for either a staged approach or a different way of addressing the problem. And the noise assumptions that you make when you're planning, you need to, when they go to the field, you need to reassess them. You need to be able to look at what they said they're going to get and see what they got. And as part of validating the whole process. The other consideration is the source location precision. That affects a lot of things. If you're going back and doing a cued investigation, you have to worry about the footprint of your cued sensor relative to how accurately you found these targets. Or if you're going back to dictum, you have to know what dig radius you're going to use. So you have to know how accurately you found the target. And again, you want to know what the maximum error is to inform the next step investigation. We talked about maximum reliable depth of detection, a little more detail here. We can, for any given sensor and any given munition type, we can determine what the signal will be, best case and worst case, right? So the worst case is under the edge of the coil, not maximally coupled to the, and the best case is vertically under the middle of the coil. We have to compare that to what we think the noise is going to be. So we have an estimate of what we think the noise will be before we start. If you don't know what it is, you need to have an estimate, you need to have a reasonable idea, so you can make sense whether you're going to use the system. And so we have the point at which our detection threshold will be, again, probably 5 times the noise threshold. And the point at which your detection threshold intersects with the worst case signal, that's your maximum reliable depth of detection. In the case here, it's 58 centimeters below the coil, 57 centimeters below the coil. That's below the coil. Okay. Understand, different deployment options will have that coil at different heights. So typically it's 42 centimeters for a wheeled EM61. Some people put arrays out, they're a little lower, 40 centimeters. Some people do litter mode where they're higher, or it's variable. So you need to know what the height of the sensor is going to be, the height of that coil above ground, to know what your depth of detection is going to be. We go ahead and do this planning. The planning should be done during the planning stage, that calculation during the planning stage of the survey. And then when you first go out on site, that's your first chance to test that assumption. You do it with what we call initial IDS survey. And you require a memo. And say, okay, we've done it, we've tested it here at the IDS location. These are the noise levels we've got. And you make and you assess what your depth of detection is going to be. Maximum. That's the first step, the first chance you get to look at it. And that way you get to look at it before you spend the money in the survey. And then you look at it again after you spend the money on the survey, because the survey can be done. Okay, the source and orientation effect on the sensor, I spoke about this a little bit. If we look at the primary field, this is maximally coupled. And when it's vertical, as you go across, the peak occurs right over top where the target is. And that's good. So we're able to locate with this sensor. This is a EM61, 1 meter square. And we can actually fairly precisely determine the peak of that. So we know where that object is. But there's another situation. And here I kind of messed up. This picture should have the ordnance off to the side under the edge of the coil. I don't know how I missed that. When it's under the edge of the coil, it's maximally coupled with the horizontal component of this field. And so you get a peak at one side or the other. The peak occurs when coils, when you go up on this track, the peak occurred because this sensor was coupled, maximally coupled here, but it gets attributed to the GPS antenna. So it's saying the peak is there because that coil is over there. When you go through the middle, it's not as large a response. When you go to the other side, the peak occurs when it's under this edge. And so you get a peak associated with that track. So you get these 2 peaks. Why is that important? Well, those 2 peaks are a meter apart. Right? So they end up being 2 picks. And when you go back to dig them, you might, you're going to find that if your dig radius is big enough, but if it's not, you'll miss it. So you have to make sure your dig radius is large enough to account for that error. If you go back to cue the sensor, and I'll show later, go back to cue the target, again, you can miss targets if you don't account for this problem properly. Adding to that problem is the effect of the coil orientation. Again, regular DGM, they don't account for the pitch and roll of the sensor. Okay, and when you have pitch and roll, not only do you have the GPS antenna offset in one direction, but your field of view is skewed in the opposite direction. So if you have a deeper target, the errors are going to be larger too. And so I don't know if you can see it, but there's kind of a graded difference here, because you'll get the peak of the curve just offset in that sense. So we know, you add all these up and you get a kind of a noise budget of 0.75 meters for that technology. Just good to know, important to know when you're planning, when you decide what the measurement quality objectives need to be, and you put in place C's. You have to understand that you're going to have misses up to that height. Okay, any questions today on so far? Did I go too fast, too slow? Feel free to stick up your hand and interrupt anytime you want, by the way. I'm going to move on and talk about advanced geophysical classification. Yeah. What is it? It's basically a principled physics-based approach to classifying the sources as being shaped like a target of interest or not. It uses advanced sensors and processing algorithms to separate the intrinsic features of the target, size, shape, material composition, from the extrinsic features. And that's distance from where the measurement was made, distance and orientation of the target level as well. And then it compares those intrinsic features to a standard library. And to the extent that those features look like a library signature, we call it a target of interest. Or stated in the opposite, if it does not closely match anything in the library, we can say it's not hazardous, as long as your library is correct. Incomplete. We've talked about this a little bit, but basically the premise behind advanced geophysical classification is saving money. It's doing less digs and saving money. That's why we do it. It's not improved detection, although the advanced sensors can help a little bit with detection. But the whole idea of using classification itself is to try and save money on a dig project. So that saving digs, you get lower costs, lower environmental impacts, lower disruption to local communities. That's what we're trying to do. There are some collateral benefits that we get. One of them is advanced classification when they invert the data and derive the extrinsic features, position, and orientation. Those positions are much more precisely known than when you just do a detection survey with a GPS sensor. That's important for some places where in Yankees, for example, they really struggle with the cost of a dig, because it's really hard to dig along the roads and things. If they have to move a little bit to make that dig radius wider, that really drives up their cost of the digs. So your digging is difficult, you want to know more precisely what the target is. The other thing that we get out of AGC, this collateral benefit, is that we actually now have a good way to QC the dig program. Right? Before it was just, you give them targets, they go dig it, and we'd say, yeah, that was kind of big enough to account for the size of the signal we had. But now we know what the target, what they pull out should be shaped like. And you'd be surprised how many times you come back and say, oh, you better go back and find the shape you're really looking for. So, it doesn't happen 20% of the time, but 2%, and 2% is significant. And the final thing, and this is what I'm kind of beating my drum on, is this associated quality management process that came with advanced classification is really going to improve our ability to plan and know what we got out of the survey and understand what residual hazard remains. Okay, the other topic, where should we use advanced geophysical classification? First one is where munitions of interest make up a small percentage of the objects on the site. We did a project demonstration up at New Boston Air Force Station where every time we put a shovel in the ground, we were looking for 20 millimeters. Every time we put a shovel in the ground, we brought over 20 millimeters. There's no sense in classifying if they're almost all targets of interest. Right? Not saving any money. And so to go with that, the munitions of interest have to be distinctly different in shape from the non-hazardous items. Or different in shape, or I should say in response, in derived response. That might have significant implications here, depending on what's happening with the geology. And then you have to be able to justify the use of advanced classification. Is it worth spending the money? Are you actually saving days to do it? If it's not working, you're not saving days. You shouldn't. Okay, how does AGC work? We talked about intrinsic features and extrinsic features. Extrinsic features are easy, you know, position and orientation. The intrinsic features, they use what are called polarizabilities, the principal axis polarizabilities, and it's really a measure of how well the object will accept or be polarized, will accept that field, the M field. And you'll find this interesting, we have the same kind of graph for the polarizabilities as we do for the actual measurements. Understand they're two different things, right? These are the intrinsic features, and I'll show you the difference in the following slide. But so we have principal axis polarizabilities, there's three of them. And for a sphere, they will all be equals, right? Because the sphere is equal in all dimensions. And for a cylinder that we're interested in, we have one big one and two equal small ones. Something with rotational symmetry. The extent that the polarizabilities are higher at the start, that's an indication of the size of the object, volumetric size. And the length of the decay, how long these decay fast or slowly, that's an indication of wall thickness. Thick walled items will decay longer. And that's valuable for us, that knowledge. And then the shape, again, shape is the ratio of the betas to each other, which is an indication of shape. So we have to use what's called the geophysical inversion to extract the intrinsic features from the signal and separate the extrinsic and intrinsic features from the actual measured signals. And it's an iterative process. So we start, if we have a sensor and a target with a given shape, we can model what the response, what that sensor response will be for that. And so that's what we did earlier when we were doing the detection phase. We're modeling how big the response is going to be at a given depth. That's easily done. And so the opposite of that is called the geophysical inversion, where you go back and you iteratively change all the parameters, X, Y, Z, orientation, and the polarizabilities. Change them all iteratively until you get a set of polarizabilities in position that matches your observed data. And that's how that works. So it's basically using the same modeling but inverting the process. Again, the output is the polarizabilities, or the intrinsic features, and the extrinsic features are positioned in orientation. To do this, we need advanced sensors. And these advanced sensors are designed to provide multiple looks at where a target and give us a much richer data set. So you need to energize the target in 3 orthogonal axes. This sensor does it by firing sequentially each element. So this sensor is built with 4 elements. This is kind of a plan view. The red here would be the transmit coil. Inside here is a receive cube. That cube has receive coils in 3 dimensions. And so the outer coils fire sequentially, and you measure the data on all the receiver coils every time. So that this gives us actually 48 transmit and receive pairs, which is a lot of data. If you think of the EM61, it gives you 1. Right? And if you set this over a sensor, I think I have this in this slide. Yeah. So if you're trying to interrogate a target, do a static interrogation, with an EM61, you kind of do 4 measurement locations to try and simulate where the 4 metal mapper 2x2 portals are. And you get a total number of data points of 16. So again, the M61 time gates are here, and the metal mapper 2x2, also 10 pads is what it's called. This is, each of these squares represents a transmit receive pair, and we get about 100 measurements along that decay curve, rather than 4. And to illustrate the concept, I have two slides here, where we have the position. This is a side view, and this is a plan view looking down of a target under the sensor. These are the derived intrinsic features. These are the measured data. And as we move that target, we notice the measured data moves significantly, right? But the intrinsic features are repeatable. And that's the basis behind doing classification. We now have a repeatable signature in that target, no matter where it is. Yeah?
Do the intrinsic features seem to change when the ordnance has been out for a long time, subject to water and swelling? And
well, only to the extent that the ordnance, the significant changes happen to the size, shape, and material composition. Of course, if it's all rusted away, the decay might be shorter because the walls aren't as thick. If it's broken apart, it might not be as clean, one big and two little.
Would they still match your library and still identify?
Yeah, actually they do, and I'll talk a little bit about library matching.
Okay.
And we'll see if it's in this talk or the next talk, but they do. And I won't, instead of getting ahead of myself, bring me back to that point. Okay. But I know I have a slide to talk about that. Okay, so the deliverables you get from AGC, you get a prioritized dig list. That's the main deliverable. So DGM, you get a dig list. AGC is prioritized. The scariest things are at the top. Things that are most like UXO. Things that are least like UXO are at the bottom. You get a whole bunch of reports about the quality of the data and usability of the data. You get a bunch of QC images to go with the reports. And then you get an immense amount of raw data. You can't just say, okay, please send me the data. It's a terabyte. Right? It's a little tricky.
DGM had that worst case orientation.
Mm-hmm.
Is there a worst case orientation or AGC?
It's the same thing. They're the same sensors, right? So it's the same thing. Right? You have the same concept, but in queued mode, you know where the target is, so you're putting it forward top of it, so you're not going to be in the worst case scenario. But if you're doing a detection survey with the new sensors, they have the same things, and it can be modeled the exact same way. And we've done that. We did San Luis Obispo. We used a TEMTAS, which is a metal mapper 2x2, as a sensor, and we modeled what its depth, maximum reliable depth of detection. That concept applies to all of them. And if you can't detect it, you can't model, you can't classify it. If you're down, signal to noise is still important. Good. Okay, so the prioritized dig list. You have, things that start at the top. Now, there's one category that's at the very top of this, and then there are things that when you took a measurement, for some reason it didn't work, or there was something associated with that measurement or that target that you can't analyze. So that would go right on the top. That's just, can't analyze. It's category 0. Put it on the dig list. We have to go dig it. We have to investigate that a different way because this investigation didn't work. Okay. After that, then you have the high likelihood. So we get a decision statistic, and that statistic is a measure of how well those signatures map a library of signatures. Go back to here. Here's where we do the mapping, where we have, the projectile in the library, and this is the tractor muffler. It doesn't really match. It matches early, but not late. But that's what we're trying to do, is match those. Oops, I'm going the wrong way. Okay, so then as you go down the list, it's kind of, it's not discretely, okay, these ones match and these ones don't. The list, you know, if you look at the prioritized list in this statistic, it generally falls off. So when you get to a region where you're, well, I call it inconclusive. It's close, but it's not, we don't know, it's probably not, but it's close enough that you can't say for sure it's non-hazardous. So you include it on the dig list. And what causes this to degrade will be the shape departing from the shape in the library. So you have degraded shapes or things that aren't really munitions but look kind of like. And you also have noise factoring into the match statistic, which reduces that value. Once you get to a point where you're confident nothing, that object signature isn't a match to anything in the library, we call that non-hazardous. And we're going to say that you don't have to dig that. And we're going to provide you a pile of evidence saying why you don't have to dig it. But that's the process. And this is called the analyst threshold. And that's an important concept to understand.
On the inconclusive digs, do you associate those with a specific ordnance type also when you're giving us that data, or do you just say inconclusive dig?
They're inconclusive. And really, you have to be careful when I did a project where I was, we give them the preliminary list and it was, okay, this matched to this type of ordinance, and they said, no, you're wrong. And it matched to an ordinance, but we have the type wrong. You gotta be careful. These are shape matching, right? You're matching things that have the shapes. So they'll give you a type, what it matched in the library, but don't get caught up in that, because some shapes are very similar. And so as long if it matched to a target of interest, it's got to be done well.
So I guess it would matter for us, because like if you say it's a 37, then we take precautions for that 37, but on the inconclusive, do we have to take our maximum greatest fragmentation distance then, because you're not associating it to an actual TOI?
So the actual software is going to, if you ask for it, it will tell you, you could say, I want the top 10 matches.
Right.
And it's going to say, I'm with a score of 90, I think it's a 75 millimeter projectile. With a little bit less certainty, it could be a 60 millimeter mortar. With a little bit less certainty, it could be something else. So it'll tell you which ones how good it thinks it matches to everything, and then it'll drop off to how well does it match up to a 100-pound bomb? Not at all. And you can ask for as much of that information.
Okay, that's my next question. Is there a standardized format you provide this information after you do the analysis, after you do the Q data?
I don't think that's standardized, because
Okay.
really, I don't think we want to make decisions on safety based on what's coming out.
Yeah.
Generally, they're going to give you the top match,
Okay.
and it's going to be close.
Even on inconclusive.
Like, yeah, leave it on inconclusive.
It's still based
on-
It's
yeah, it's still
matching
based on
something.
something.
So you're
Yeah.
getting a size match, but sometimes if you look at it, it might get to inconclusive based on the ratio of the primary to the two secondary birds, and the size might be way off, but that ratio is good enough to make it match something. So the high fits are pretty good indicators. In here, I don't think I would compromise safety based on what information you're getting. That's a really good question. Okay, some examples. This is what I was talking about. We have a high, is the decision metric. It fits. I don't know how well you can see these, but these darker blues and reds and greens are the actual library items, and the library that's being matched to, the library items, are lighter shades in behind. So here you can see, the light blue just above, but that's a pretty good fit all the way down. This line I've drawn here, that's where we stop looking at data. So that line isn't included in the conversion, in the match repeat. So these two are two examples of really good fits. These two are two examples of very poor fits. The three polarizabilities are equally spaced apart here, and there's equally spaced apart there. They're not indicative of anything with rotational symmetry at all. In here, this is the tricky one. This is where we have something here where this isn't indicative of any kind of a target, but its decision metric is similar to this one. That is, this one has a degraded decision metric because of the noise. And so we have to put the threshold low enough to capture this, even though we're going to capture a lot of those. That's just the way it works. The only option to doing that is having someone go through and making qualitative judgment, and we don't allow that in the new paradigm, because qualitative judgments require, they're prone to human error. So we want to do everything based on objective numeric criteria. Okay, so when we do these projects, we have something called analyst calibration digs, and what those are a preliminary look at what is actually out there. And so the analyst will say, hey, I need to know what these 80 items are for. What actually, I have these signatures and I want you to tell me what came out of it. And we use them to inform our dig, no dig decision, right? Because up here, oh, I should have done here. I'm going to ask them to dig that up. Is that really something of interest? Because then it means I have to push that threshold down lower. If I have a bunch of these but they're nothing, I can leave the threshold a little higher. Okay, so I also want to validate my library. We have a library, to the extent that if you have something out there that's not in your library, you're not going to find it. But what we do is we go through a couple of different analyses. One is called cluster analysis, where we look at all the signatures and we compare them to each other. And we look for clusters of like signatures. And those are things that are ubiquitous, obviously shapes that are ubiquitous to the site. And if they're ubiquitous to the site, we want to know what they are. So we'll go and dig a few of those and just make sure we're not finding munition there that wasn't in the original conceptual site model. The other thing we do is we do what's called feature space analysis. Okay, so that's, again, I got ahead of myself a bit. Here's the animal threshold determination. So that's the decision threshold being that we decide where our dig, no dig is based on how many of our targets that we selected for those animals threshold digs, where they occurred, and we remove that threshold. Cluster analysis, here's the results of the cluster analysis, where we found clusters that are out there.
Is the software making that decision, or one of the geophysicists?
This decision?
As far as which clusters are to be looked
Oh,
at?
the software will find clusters for us.
Okay.
Yeah, so you have certain parameters and you say, okay, do a cluster analysis, and it says, okay, I recognize 18 clusters. There's a minimum number of 5 or 4, the population of 4, these 4 items look alike, and we say, okay, I want to know what they are. And what, okay, so we go through, and what we would do is I include, all of the seed items that you put up. You should include that in the cluster analysis. It should find those, right? Just to know that the cluster analysis is done. So and then you go and dig samples, because you really want to know what's out there. And if it comes up as a target of interest and you don't have in your library, you need to add it to the library and rerun the whole library matching. We do the same thing with feature space analysis. And feature space sounds, all funky. All it is we go here and we find out what the size is, map size versus decay. That's the wall thickness. So here, this is the map of size versus decay. This is where all of our library items. We're looking at this project. We're looking for mortars. That's where all our mortars sat in this quote feature space. And we said, okay, anything with size below a certain threshold and decay below a certain threshold, it's going to be safe. We don't have to worry about it. But if we find things up in here that are in this feature space that are not matched to a library item, we want to know because it's big enough and has a decay long enough to be a possible target. And we look at the 3 features. We do the same thing with symmetry. So we say, okay, if a target is large enough, has a long enough decay, and has rotational symmetry, it's shaped like something of interest, so we're going to go dig it. And we dig those as part of the analyst calibration digs. So the last thing we like to do with the analyst calibration digs is it actually is an initial validation of your results. They go and dig some, and if they should get, if you have something like that, they should get an answer like that. That's what we're looking for. We want to say, yes, the system's working. Or more importantly, if we get something like that and not getting that, we have to find out why not. Any questions on AGC? We good? Okay, let me go back and we'll revisit the DGM. Got a question here?
Yeah, can you go over geophysical noise?
Geophysical noise?
Yeah, on multi-vote app, how to talk about how to, because you had said you have to go in and first to find out about what's your, I guess, iron content of the soils?
Well, you could do it that way, or what the smart way to do it is take the sensor you want to use and take it to the site and see what your noise profile is. Because that's what you're going to detect.
Because there are some thresholds for that, yeah?
Well, your threshold, there will be, I mean, you go back to the whole planning process and go, oops. Go way back up. We'll go to that one slide.
Yep.
Because this again is,
That one.
it's critical, right? Because if you go in and find out your noise levels are up here, so now your detection is here, you know, and if you're, if you're only seeing things on the surface, you need to know. But the whole, it's really hard to just go and measure iron content and decide what the noise for your sensor is going to be. You really have to take the sensor and the configuration you're going to use it and determine what your noise is. And hopefully, if you're doing a removal action, you have some data from the RI that you can use to determine what the noise is. And the RI should give you enough information, particularly here, the problems you have. The RI, one of the main focuses should be on characterizing the geophysical response at the site, because it's going to change from location to location. And how granular that changes will be very important for the success of any geophysics on your site. The problem with the noise here isn't just that it's noisy so you pick more targets, is that the noise can mask a target.
Does that noise affect the AGC differently than the?
No, well, you can't detect it, you can't do AGC, right? AGC will not see through the noise for you. Noise is noise, and that's a limiting factor. It's a limiting factor that has to be solved before you think about AGC. All AGC is trying to do is save you digging, right? That's all it's going to do for you, is save you digging, and give you some side benefits, but it's, you know, if you can't, I'm sorry, go ahead.
No, what if the noise is too high that you really can't detect anything?
Then you need to use a different approach, right? I mean,
what is
don't blame the
different
geophysicists, we didn't
Yeah.
put it there, but it doesn't work.
What
right?
is the different approach? Because
Well, you know, mag and dig, dig and lift and dig, scrape, or fences, you know, seal off.
So remember at the very beginning when I said we've got 3 ways to address munitions risk: removal, removal of the hazard, keeping the people away from the hazard, or managing the exposure. If removing the hazard is a technical challenge, then you might have to look at the other 2. Or if the other 2 aren't an option, you might have to look at a much more aggressive way of removing the hazard. You might need to look at, instead of using geophysics to detect, you might need to do excavation. You might need to dig the soil. Now, in a lava field, is that really practical?
In a lava field, is a munition buried?
I don't know.
Is that, I don't know, I don't have any experience
Or
with
in,
lava fields.
yeah, so I think the important message is if there's site noise, it's going to be a technical challenge, and you've got to take all of that into account when you're looking at the bigger picture of how to make the site safe. You don't get it, it's not as straightforward as a site where you don't have those technical challenges, so you just got to pay the money to do the removal. It might take additional effort. Not the best answer.
I was
but
afraid of that. That's all.
there's no silver bullet for high noise site right now.
So you mentioned doing some demonstration project using AGC. Have you done any demonstrations in Hawaii? And
There have been some that have been done, and it depends on, and I spoke to one of the people involved in it, and their success. They were done as demonstrations, not as projects, so they weren't done with the quality management system behind it, so it's hard to assess whether they're successful or not. They say they're successful, but without that quality system management approach, you just don't know. They've demonstrated it, and they can technically say it worked here and here, but you have to go through the whole process. I know they said some sites were much more challenging than others. Some worked well, some didn't. I read one of the reports where they actually missed a 60mm seed, and I looked at the depth, and they missed it due to signal to noise. It was deeper than what they should have, but they didn't address that because they didn't have a quality system. They were just coming up and demonstrating. And when you're doing these projects for real, you can't just go out and demonstrate. You have to actually work to a system. You have to have a plan. You have to predict what you're going to do and then follow it up. And that's the only way you can tell after the fact how useful your data.
So the studies you referred to, that the one done by the STCP?
Yeah, I believe so.
And generally speaking, I mean, people realize that the geology in Hawaii is high in iron.
Yeah.
So it creates the background interference. But in your experience, have you seen any less in weathered basalt or non-weathered basalt? Is there?
I don't know. I mean, it's going to be site by site. What I'm told, I was on Kalahari in 2001. You know, but we're just trying to get a sense of that would work, you know, marginally. So all I have is kind of anecdotal evidence, but certainly there will be sites that are not doable. You really have to have an understanding. The trick is finding out how to delineate those sites and how to find, you know, quickly, and so we all know, because that makes a big difference. So not only have your use, that you delineate things by use, but you have to know what the geology is to delineate by, and what the terrain is, because if you have to have these sensors a little bit higher, that changes things drastically.
Yeah, I noticed your pictures, all nice flat areas.
Because that's where they did it first, because it's been done in challenging terrain, but you really have to understand what you're getting.
We have a project that will be using DGM at a former firing range in a field of 50 cal rounds, but our target of interest is the Mark IV grenades. What is the likelihood of successfully identifying the grenade? Or shall we just ditch the DGM and go to mag and gear?
Well, so when you're talking DGM, you're talking just detect, not identify, right? You're looking for detection. Like there's DGM is detection, and then AGC is classification, is identification. So I wouldn't know, right? You know, I think that you want to have, somebody should get a sensor and take it out and see what the response is.
That's in reference to peak site. But just for myself, I'm thinking, your site, the soil content is more quality material.
Right.
You know, so it may have a really good chance to be working on this site.
Yeah.
Versus some of the other sites that work at higher constant. I think the geology is really important to look at on your sites.
Because we know what the response will be for a given coordinate study. We just don't know what the noise is. That's a $24,000 question.
And that noise could be not just from the geology, but also from just the amount of other metallic debris.
Yeah, so if you're at a site where you have, there's so much metal there, that will also be a problem. Using what we call that is a saturated response area, where you get signal everywhere. And the way to handle that is you actually have to go and do the mag and dig, and then do DGM after that. So you have to get rid of the metal first. Okay, so this is an associated topic, but this is doing detection with an advanced sensor, basically. So the sensors do have certain advantages, and that is on sites where when we do regular DGM, we're using what's called amplitude-based detection, amplitude response detection. And so anything over your detection threshold in the let peak, you have to go mark that for further investigation. By definition, that gets you a lot of small targets that are closer to the surface relative to your smallest target of interest that might be deeper. And you end up having a lot of extra digging because of the small targets. What we want to do with the advanced sensors is say, okay, using the dynamic data, can we do the same kind of inversion and separate the intrinsic features and extrinsic for that, and decide what we're going to do based on the intrinsic features. We can exclude small targets and deeper targets. They've found this to be relatively, pretty successful. I don't know if I base a whole cleanup on doing that. You do it, and then you have to go for targets that you didn't get good inversion results for. You have to go and queue them or technique. But certainly, it's a way to reduce the number of targets that you actually have to investigate after the fact. And it makes a lot of sense for an area where you have a lot of small metal, discrete pieces of small metal littered all over the place, and you're looking for something much bigger. It makes a lot of sense to do.
So the way I like to think about that is, if you're taking the advanced sensor out and you're doing your primary detection survey with it, it's collecting all that extra data. That'll allow them to screen out the easy answers on both sides. The things that are obviously an intact munition they will generally know that from this level of data, and they'll be able to say, we definitely need to do those. On the other end, these small pieces of metal, the small fragments on the surface, are obviously not of concern, and they can sort those out as well. So that then after they've done that detection survey, to go back and do the queued survey, they have a lot less area, a lot less flags to go back and queue, because they've been able to do that triage of removing the obvious ones and only focus on the harder ones to answer the question. And it's been extremely effective.
I don't know if we have to go through the details of this too much, but basically the way it works is we go through a first step where you do amplitude response detection, and you get these bumps that we saw. And then it goes and inverts the data to try and get, using a number of different inversion routines to try and find information about the sources. It will merge the co-located sources that are obviously from the same target, merge them together to give our final list of sources. And then, based on the size and decay, you can get rid of all the small stuff. And, identify things that are obviously targets. The other advantage you get from this, and I alluded to it earlier, is the source location precision. If you're using this method, you've inverted for the sources. Now you know your source, you know the extrinsic features, the locations much more precisely than this blob will come. So instead of being within, 0.6 meters, now you know within 0.2 meters. That makes a big difference, depending on what sensor you use. When you're going from a DGM survey, and you're going to go and do a queued investigation of those targets. You have to make sure your footprint matches your the error or your precision of the initial anomaly position. And to illustrate that, here we have, simple. There's this purple radius. That's the EM61 detection radius, and on nice flat ground. And the sensor target, there's a measurement quality objective radius where you have to put that middle of the sensor to within 0.2 meters of the flag location. Right? And so you have these two errors that add up. If they add up in the wrong direction, which is here, in this blue shape, the shaded blue shape, that's the actual footprint of the sensor. if you have the sensor offset in one direction, but offset by 0.2 meters, that's kind of the precision you can get when you try and require things. If it's offset in the wrong direction and you miss that target in that direction, you can actually not cue the target. So, informed source selection with its enhanced precision prevents that. Worst case scenario, you still put the target. So the takeaway from this is if you're going to do cued survey, it's really good to do the initial detection survey with an advanced sensor. Downside, right now the advanced sensors are more expensive to use, but that may change in the near future. That will change in the near future. You'll get arrays of advanced sensors that will be appropriate for doing these type of surveys.
So what's the cost comparison between an advanced sensor and AGC? It's about the same?
No, the advanced sensor is
The AGC sensors that's an advanced sensor.
Oh, that is.
There was the hand portable one compared to the one you had on the.
Well, right now there's two basically that are kind of commercially available. One is they call it the Metamapper 2x2, which is the 10 pads, which is the one I was showing here. And then there's the MPV, which has been out here and has been demonstrated out here. And that's handheld, and that's actually relatively efficient, you know, compared to even what the Chemtest or the Metamapper 2x2 was in terms of production rates. It was surprisingly efficient. Saw the demonstrators. But what we need in the industry is an array, so you can do projects, larger scale projects. Like they have arrays that can put like 5 or 60 months together, and that saves a lot of money if you're doing 3-meter swath rather than 1-meter swath, and or half-meter swath. So the industry actually needs an array that can get these results, but do it as cost effectively as with the EM61.
So I'm seeing a lot of the companies propose the EM61 for their dynamic collection. Is that cost based? You think that's what it's doing? Okay, all right.
And this is a problem that we're going to have to hold our feet to the water, or toes to the fire. It's happened on a recent project down in Wall. Basically, they have to overpick to account for that.
And then how do you, I mean, especially out here with our issues of clutter and geology, we get giant pink blobs. Where do they go queue then if they do their dynamic collection with this?
Yeah, if you get a giant pink blob, I think what you have to do is you have to just circle it and investigate.
Right. So we're gonna have to go into with a planned approach of AGC, and then we're gonna have to delineate mag and dig areas throughout as we realize which areas it works and doesn't throughout the life cycle of the project. Though.
And with more precision and more granularity than you normally would.
Right.
It used to be, oh, this region is, but no, right, really, if you get that, and we're coming up with ways to delineate those automatically. You really have to, if you get a blob big enough, you put a circle around it and say you can't. Because if you have more than 3 targets under the sensor, the AGC doesn't work very well. So if you have that kind of density, where you get 3 targets within 1 meter, or one square meter, that's the problem. Or 4 targets, and then it becomes a problem. So you have to have a way to identify that kind of source density.
Yeah, in your experience, when you come across challenges like that, how do you get around the contractor bid for something?
That's really hard, because right now it's performance-based contracts, right? So they're responsible for everything, right? And that's why your bids are high. Right? So to the extent, and this is kind of a keep in mind, to the extent that you can provide enough information to bound their risk, it's important, right? Or take some of the liability out of their hands and documents, because you're building in a lot of contingency that gets crazy. It's just a waste of money, right? So if you take the risk, because it's a risk that's there, somebody has to take it, right? If you make the contractors take it all the time, you're going to get high prices. So you have to have an exception to the rule, or have something, and I'm not sure what the answer is, but if you understand that the process should be to bound these things and mag and dig. And guess what? If you get those circumstances where you do not have, you cannot clear it so that you're confident that it's protected environment and health and safety of people, that's the problem, right? If they're responsible to do that, then that's where they get really high numbers. So you should be able to bound it and say, okay, you need, this is a standard you have to work towards. And I don't know how you do that on a performance space contract.
Right.
But I'm sure it's fun, right? But I think it's something that's worth discussing. And the more risk you fill with the contractors, the more they just have contingency.
We have a situation here with white phosphorus, and you could probably give more details, but as I understand it, there's a situation where there's fragments that still contain white phosphorus that might be overlooked by AGC.
If they're not of a shape that's in our library, then we will.
So if that's a situation, if you have an area where you know they were using that white phosphorus, you wouldn't recommend using AGC in that area?
That's something when you're saying you're either giving them the risk and say they have to worry about it or using it. But, what are the shapes? How big are the shapes that contain it? Does it just stick to the inside with small pieces, or, if that's the case, then.
The residual risk, I don't think is necessarily high enough to warrant that being a reason to not use the technology.
Okay.
But on that same note, will AGC classify fuses, boosters,
Right.
things that still have
A
explosive
low
gases?
ordered munition, half the TNT is still in my 155, but my shape's completely different.
It depends how completely different the shape is. I've seen some shapes that are pretty bad, but they still match.
Okay.
Because of the noise issue. We included fuses, like PD fuses and things that they're big enough. I think once you get down to the size of a 37 millimeter or a hand grenade, that's kind of the lower limit. I don't think you can, 20 millimeters, I don't think you want to.
So kind of 37 in a tough geology is really.
I'm not even sure 30, I'm not sure
Well,
what's.
and you also have to keep in mind what else is out there.
Right.
So if you've got a 155 range where you've got a whole bunch of fragments that are all generally the same size as the fuse you're looking for, you can find the fuse, but you're going to be picking up a whole bunch of fragments that happen to be in close proximity of size and shape to that fuse. If you've got 37s and 155s on the same round, the same range, you can go after the 155s and pull them out really easily because they're big and different. But those 37s are going to look a lot like the fragments from the 155s. And you've got thousands and thousands of fragments from 155s intermixed with your 37s. You may end up digging a whole bunch of fragments to go after those 37s.
So our inconclusive digs, a lot of times are you finding those are fragments that are.
Yeah, those are things that are shaped kind of like,
characteristics.
yeah.
I mean, we still got that same decay kind of.
It's not that it's indeterminate. It's just that fragment is the same general size and shape as a 37 millimeter. So you'll get a decent match in your library.
Okay.
Just to account for the noise.
Yeah, it looks like a beat up 37 millimeter.
So
The other thing that some people are doing, like in Vieques they were talking about, is using classification to find the big things, and so they can armor up for the small things, and be a lot more successful in cleanup.
Yeah. Okay. And then the other question I have, I guess, so we have the engineering controls you talked about, like the MOFB and the OFBs. Our threshold for when we're allowed to use those and not is dependent on the type of ordnance, the next weight, and those types of things. With with an AGC platform, I know with an M43 I can use my MOFB, and with an M56 I can't. They're both 81 millimeter mortars. Are you going to be able to tell me this is an M43-81? No. All right.
They're the same shape, or roughly the same shape.
They're completely different lengths, but they're both 81 millimeters.
The different lengths you might be able to, but
And should I trust that data?
No,
if I got
no, this
okay,
is not designed to, you should not make safety decisions based on this one.
I would say look at the libraries for the two items and decide how different they are and how confident you are between them. But you would have to really look at.
So what happens if you get one that's kind of lost its tail? So it's the same shape as the other, same length as the other one. So that's what's a problem.
So what you just said was you wouldn't rely on the AGC to make your safety decisions.
Correct. Not with respect to dig radius. Once we've identified it as something that's hazardous, I don't know, I trust what it called it to make for my exclusion ratings. Right? Certainly, if you people have a non-hazard, that's a safety decision, right? We're leaving the ground.
Right.
But, you know, if you're deciding, you know, what your exclusion radius is going to be, the exclusion zone is going to be based on what the software spit out. Because we're not doing anything to monitor the quality of that, right? We're not saying that we're telling you dig or don't dig. That's the decision that we're standing behind, and all our quality systems are designed to answer that question. They're not designed to tell you how precisely we're naming that target. We do nothing quality-wise to give you that information or to test that. So by definition, if that's not managed with respect to the quality system, you shouldn't be relying on it.
So is there no feedback, like the AGC? I don't know, AGC is that just one company?
No. AGC is just it stands for Advanced Group Classification.
Right. So, let's say it's at 95% that it's this piece of munitions, and they got to dig it, and it's something different. Is that reported back and then logged into the library?
Every dig has to be reviewed by the analyst, and it goes towards validation of the approach of what you're doing. And so if it's a significant departure, they need to answer the question, why? Why was it that, not that? But you can have things that, you know, from an outside looking in, that should be obvious, but geophysically, those things are very similar. And so, you know, that's why you have the analyst doing the comparison, not the UXO Technology or somebody else. Because you can get in the world of hurt.
So if the AGC were to say this is a 37 millimeter round with a high confidence, and the guy goes out and digs it and finds a 155 round, that's a failure. Or the other way
Very
around.
good trouble.
Now, if AGC says it's a 60 millimeter mortar, and they go out and dig it, and it's a 75 millimeter projectile, those are fairly similar. So then you're going to ask, why the mismatch? And it might be that with the noise that the second best match was the 75 millimeter. And then you say, well, okay, you got it right enough. But it's really that quality check of going back and looking.
Or maybe the curve degree was too early to find the distinction.
And I'm going to actually flip it on its head, and at the end, when I'm talking about regulatory considerations, from the regulatory perspective and the safety perspective, I'm much more concerned about the don't dig decisions and how to QC and how to verify the don't digs, because those are the things being left in the ground. Once they decide to dig it up, as long as we make sure that they dug up the object that they were going after, that's good. That's good. We decided these items are safe to stay in the ground. We're not going to dig them. How do we make sure that we're confident in that decision? So the analysts are very focused on finding and picking the things to dig in order to make sure that we get all of those, and we have to be comfortable with the things they didn't pick.
But you know, at that point, from a regulator perspective, is Department of Health planning to come out with some QA requirement for oversight of the contractor or oversight of the Corps of Engineers or something like that? And what kind of certification is that going to be? Any certification going to be required for that QA?
That's an interesting topic. It's a topic of discussion.
That
It's
is
being
a-
worked on. It's an important one.
I can't speak for what Hawaii Department of Health is doing. I can say that a lot of states are looking at that very question and looking at how to do regulatory oversight of a very technical process that requires very specific expertise, and how to make sure that we're fulfilling our regulatory missions. So It's a question, it's a new technology, it's an innovation, it's a change. What's the appropriate role for the states? What's the appropriate role for regulatory oversight? What's the appropriate role for quality control, quality assurance oversight? For how do those interact?
So the same group that developed QAP, Jordan Nelson, is it EDQW?
IDEQ?
I'll find out with it. But they're now trying to wrestle with the problem. How do we assign, or how do we certify, and using a small c, not a certification. How do we know that this person is qualified to do over this oversight? They had the same problem when they started the accreditation, the DAGCAP accreditation program, because the accrediting bodies didn't have the technical expertise to oversee it. And what they did there, they selected 4 people from the industry and said, okay, these are people we're going to assign, we're going to call them technical assessors. And there's a little uproar because these people, I was one of them, but these people are, we all work for different companies and we're competitors, and so people who didn't get something selected from their companies, hold on, does that mean we're not going to get accredited? But it turns out they do, because the whole accreditation process is evidence-driven. It's not judgment. It's the whole thing we're trying to do is evidence-based decisions, weight of evidence, not professional judgment.
So currently, no state in the U.S. has any kind of regulator QA process.
In Colorado, we did the first live site full demonstration of AGC where we ran it as a removal action. At the end of the day, not digging things that were on the no-dig list and doing that as the cleanup. We hired a third-party expert to help us with the QA of the data. We did not have the in-house capability to take AGC data and process it independently and verify that what they were doing was working. So we hired somebody to help.
As a shameless plug, my company was formed to provide that role. So no.
Yeah, it's an important question to be looked at because as the state, you've got to be sure that you're confident that you're doing your job. As the Army Corps, you want to be confident that everybody's doing their jobs efficiently. You don't have unnecessary overlap. And yeah, you want everybody to be educated and informed and working towards the same solution.
So we found in doing these projects that an integrated and invested project delivery team is really critical. Because right at the planning process, you have to know what you're getting. You have to be involved. And people with concerns. If you don't involve people at the start, you have to try and convince them at the end. It's much easier to get buy-in, go through the process, and be as transparent as possible. Performance of any system can be modeled and predicted and validated. This can be done. Whether it works or not, we should try and model it ahead of time. We should try and get our predictions as close to reality as we can. But it can be done, and it should be done, and it should be validated. It has to be validated when it's done, so you know what you got. And again, ultimate success requires detailed plans and adherence to the plans. And we'll talk about that tomorrow when we talk about quality considerations. Anything else?
So it's quarter after. We'll break early for lunch. Back at 1 o'clock. We'll go over the life cycle of a munitions cleanup project